start. Welcome to Unit 3 of COMP526, Efficient Algorithms. We'll look at sorting in detail in this unit and a few other related divide and conquer algorithms. Much of this first part will be repetition for many of you, but then we'll have two more parts that go a little deeper and is also touching on some of my own research, so it's kind of dear to my heart, the topic. But let's get started slowly. And before we get started, let's have on the record again the little overview of what sorting algorithms people already know. Bubble sort is really big. For some reason, bubble sort is always well known, even though it's by all means, by all standards, a not great algorithm. It's fairly slow. But it somehow is cute and has a good name, I guess. Good names are important. The other two big ones are quick sort and merge sort. We'll talk about these. And okay, many other little variants, more or less well known. Heap sort is, of course, another one. That is taking the binary heaps that we use to do sorting. If you haven't seen this, you can you learn a little bit about this in the tutorials. And we'll come back to this guy as well, radix sort. There's actually many more. It's sorting is somewhat of a standard toy problem that people love to invent new things for. Whether or not each and every one of them is useful is maybe a secondary question. This is often something that people do for fun. Some form of fun, I guess. For this module, what I'd like what I'd like you to take from it is specifically merge sort and quick sort as the two most important and the most important efficient algorithms that are in wide use. Know what their performance characteristics are. And then we'll talk briefly about the lower bound for sorting. Again, something many will have seen in undergraduate computer science courses if you've done that. And we'll briefly talk about how you can break that lower bound. And then we'll look at what happens if you can exploit some existing order in the input. So there's the overview of the sections. At the end, we'll cover a few other divide and conquer algorithms, just to show you that many of the concepts that we apply to generate sorting algorithms are more general than that. It is insightful to have a few examples that are beyond sorting for that. Why still do sorting? First of all, it's a fundamental problem that still has unsolved corners. For example, an innocent question could be, what's an algorithm that uses the fewest number of comparisons to sort n items? And kind of tantalizingly, this is open. We don't really know. At least if you zoom in very closely, if you want to know an algorithm that exactly uses the minimal number of comparisons, that's open, and the last substantial progress might be from the 50s, 1950s, with a few improvements after that. But that's kind of the academic motivation. Of course, sorting is a subroutine that's used for many other more complicated algorithms or processing steps. It's a way to remove duplicates from a data set. There's other ways with hashing, but sorting might be faster in some cases. And many geometric algorithms, things like scanning line algorithms, often use sorting as a pre-processing. What we'll focus on here is the classic fast sorting methods. In the first part, just as a recap, how to exploit if the input has some structure to be faster. And we'll also talk about parallel algorithms and parallel sorting as one specific topic, but not in this unit. We'll come back later to parallel algorithms and then look at sorting again as one problem where parallel algorithms are interesting. Because sorting it's possible to parallelize it, to use several cores on a computer to sort, but it's not obvious how to do it. before we start, let's cover a few basics and define what we mean when we say sorting. And for most of this unit, this will be the setup, with one exception that I'll comment on when we get to it. We'll work with arrays of objects, and I'll be generic what objects are. It could be anything. Think of some arbitrary Python object if you want. I've used this a little bit before, but just to state that formally again, if we have arrays, I use this kind of notation with dot dot to indicate that that's a range in the array, or that the array has this size. Python would probably rather have a colon and then the two indices. I'm trying to use this notation often where the first index is inclusive and the second is exclusive, which is exactly what Python would do with a colon. But I'll use these parentheses to make that visible in the syntax. Whereas it's standard if you use square brackets that it's inclusive on both ends. So that's just so that you don't misread the pseudocode that comes. What we assume as well is that the objects are somehow ordered. We talked about this for binary search trees and heaps already. It's the same assumption. So there's given two objects from our array, there's a way to tell which is smaller. Now here we'll be happy if this is just a lesser equal operator. So you can ask, is this lesser equal than this? Yes or no. That's what we'll work with. Python has, of course, this built in as lesser equal operator. You can override it for custom classes by implementing or overriding this function with a double underscore. I don't know if you're new to Python, maybe you don't know this yet. It's just a way to define the lesser equal symbol to mean something for your custom objects. Java has, as the second language that many people know, has a similar setup. So there's a specific interface comparable that you can implement. And then objects have a compare to method that behaves essentially, if you compare it with 0, it behaves like the comparison operators. So long story short, given two objects, I can decide which one is smaller. And then the goal is to rearrange them in the array so that they're in sorted order afterwards. So unless it's otherwise stated, we'll assume we sort in place. So we produce the sorted list in the same array that we're given as input. That doesn't say that some algorithms don't use extra memory to do the sorting. But at the end, it should be back where we started. Right, for the experts, we'll focus on internal sorting, which means methods that are effective if the input is fitting in main memory, small enough to be held in one computer and in main memory. So that would be a few gigabytes easily. On a large server, maybe a few hundred gigabytes. On a large server, maybe a terabyte. If it's much more than that, then you probably use different algorithms, and that's a separate topic that we won't touch on. We'll also assume for now, for this unit, that we're just doing everything sequential, single processor. Apart from asking you just for names of sorting algorithms, let's do the slightly more theoretical version of this. I will comment a bit more on what this question means. Had 111 people vote earlier. Let's see how close we get to that. I don't know why this picture showed up. I didn't intend the picture to be part there, but if you recall, that was part of the prior knowledge survey as well, and that's where that screenshot is from. Let's leave it with that, so you can see various answers. Yeah, if you sent the letter from before, then you'll have to look up what that stood for. Not very convenient to do. Yeah, sorry, I'll have to remove that image. That's just confusing. So the most voted answer was G. If I hide this again, G was order n log n, big O of n log n, and then various other things. So let me unpack the question first. There's a few things that maybe we haven't spoken about in full detail yet. I'm asking about the complexity of a problem. That's a bit of a weird thing to do, right? We've talked about the cost of running an algorithm, but this sorting is not an algorithm, that's a problem. It's an algorithmic task. So what do we even mean by complexity here? What algorithms people mean in this context is, give me the best you know about this problem, how fast can you do it, and what's the best impossibility result you know about that problem. And for some lucky problems, and sorting is one of them, we have matching upper and lower bounds up to a very small error margin. So we know precisely how well we can do, and we know ways to do that well. That's pretty striking. It's one of the things that computer science is fairly unique at. Show me some of the other engineering disciplines where you can have so close gaps between what's theoretically possible and what's actually achieved in practice. I always bring this example of an internal combustion engine, you know, a car motor. We know there's some physical limits like preservation of energy or things like that, but we're far away in the efficiency of actual machines, in actual engines from that limit. Computer science for sorting and other problems, we're right at the limit. There's a theoretical lower bound of how fast you can go, and we're almost matching it. That's pretty cool. So that's what people mean when they ask about the complexity of the problem. Give me the best impossibility result and the best algorithm that you know, and hopefully these are close. For sorting, well, we know that we can do it in n log n time, and we'll come back to that, of course. We also know there's a lower bound of n log n. And those essentially match if you're only looking at the big O classes. So you could say the complexity is theta of n log n. And what this statement means, there's a lower bound of omega n log n, or impossibility result, you can't do better. And there's an algorithm that achieves this. And those two things together, so if you have these two, they imply that you can say the problem has this complexity. That's what you will read in more academic writing about algorithmic problems. I thought it's useful maybe to mention this. Now, we haven't talked about this, we haven't talked about this, so these are both results. I just claimed that these are known, but we'll actually cover them today. It's not so far away.